Hi everyone, this is our lesson on nonlinear inequalities. You can find this at the top of page 10 of our Unit 2 notes packet. Nonlinear inequalities. You guys would have seen maybe some quadratics last year in Algebra 2, but mostly you would have dealt with linear inequalities back in Algebra 1. We solved back then for when a variable was greater or less than a specific value, but now we'll extend that thinking to more complex functions. We are going to focus on critical points. All right, and what do I mean by critical points? Zeros and any vertical asymptotes. All right, those are the things we need to be hyper aware of when we approach these inequalities. In the functions that we need to evaluate, we will find all critical points. These normally include intercepts, maxes, and mins, but what we really deal with, as I said, are the zeros and the asymptotes. Now, let's take a look at an example. The way we want to approach these problems is we want to set this inequality unequal to 0, solve the related equation, and then test some points. So let's zoom in on example A. We're going to start by moving the 15 over to the left side of the inequality. Oh, sorry. This is what we're looking for. We always want to compare in relation to 0. More than anything, that's just an easier way to compare values. It allows us to make some tests very quickly. So now I'm going to try to factor this, and I do believe this is factorable. We're going to get 2x minus 5 times x plus 3. So our solution set is going to be all the values of this factored expression that are positive, right? Why are we saying positive? Well, it just needs to be greater than 0. Well, this function equals 0 at 2 locations. We can see from our work so far that at -3, there is a 0, and at 5/2, there is a 0. Just a different tip here that I think can be useful. As we set up this number line, I think it's useful to just make note for yourself whether or not these endpoints would be included in your solution. I used a blue open circle there to indicate that the endpoints would be excluded because we have a greater than symbol. Well, what we've created are three unique intervals where this polynomial may be positive and it may be negative. So we need to test with specific values in each of those intervals. We know on interval 1, which is to the left of -3, we could choose anything. I'm going to use x equals -10. When we test here, we don't need the specific values. Because we've made everything in relation to 0, we're really focused on the sign. If I were to plug -10 into my two factors here, I would get some negative number times some other negative number. We could find it, but it's not really useful or meaningful because we know that two negatives create a positive, so that interval 1, will be part of our solution set. Interval 2, what I have labeled on our number line there, falls between -3 and 2.5, so I'm going to use 0 as my test point, and what I find when I test this is I will get a negative value times a positive value. Well, we know that a negative times a positive is negative. We're looking for positive values, so that interval would not be part of our solution. Now we're going to test our third. Our third, again, I'm going to use x equals 10. It's arbitrary, just a large positive number, and what I find is that I'm left with 2 positive values, and when we multiply positive values, we get a positive product. So all of this work we've done so far, all we have to do is answer the problem. So where does x make this inequality true? Well, at 2 different intervals, interval 1 and interval 3. Interval 1 goes from -infinity to -3. And interval 3 goes from 5/2 to infinity. So basically, this graph looks something like that. Or obviously, we're just taking a kind of a quick, dirty look at it. But what we can see here is that there is a point, there are two sets of points where we can make this inequality true. I am going to demonstrate letter C as well, just because there's some more complicated factoring, and then I'm going to let you guys try the two problems on the right on your own. I'm going to just walk through example C now. So again, I'm going to start by setting my inequality equal to, not equal, but you get the idea, to 0. And then I'm going to factor to find my possible roots. X squared, x plus 1, minus 4, x plus 1. I'm factoring by grouping here. I have x plus 1 as my common binomial, and then I have x squared, if that's not clear, x squared minus 4, which will factor into x plus 2 and x minus 2. So in this situation, we're going to have to test 4 intervals. All right, so we set up our number line, and we're going to go left to right. We'll have -1. Oh, well, we should start with -2, then -1, and then +2. So in this case, we're going to test 4 different intervals. So let's see how that looks. So our first value, for whatever reason, I like plugging in -10. And if I were to plug -10 into each of these factors, I would get a negative times a negative times a negative, which is negative. And we are looking for a value that is less than or equal to 0. So this first interval works. My next interval is between -2 and -1. That's kind of a tricky interval, so I'm going to use -1.5. If I were to plug that into my first factor, I would get a negative. My second factor would be positive, and my third factor would be negative. When we have 2 negatives and a positive, we would have a positive result. So, and we are looking for a negative result. 2 is not part of our solution. Interval 3, I'm going to plug in 0. That's a nice easy one, between -1 and 2. When I plug in 0, I get a positive times a positive times a negative. 1 negative will lead us to a negative answer, so interval 3 will work. And then finally, we can plug in our final fourth interval. I'm going to plug in x equals 10. All 3 factors will be positive. That will that results in a negative. And 3 positives will result in a positive. We don't want positives, right? Remember, we are looking for values that are less than or equal to 0. So the 2 intervals here that work are intervals 1 and 3. Interval 1 goes from -infinity to -2, and because of the less than or equal to sign, we're going to use a square bracket. That will be in union with our third interval, which will include the endpoints -1 and +2. I'd like you guys to go ahead and try examples B and D on the right-hand side. I'm going to fully work these out while the video is paused, and we'll kind of debrief quickly to see how you did. All right, with some movie magic here, we can see our work for problems B and D. So B was a little bit of a mean one. You can see here, this quadratic, not factorable. So we had to solve another way. I chose the quadratic formula. And what I found was that the 2 zeros were -1 minus √5/4 and -1 plus √5/4. Just as same as the other problems, that creates 3 different intervals, and we plug in values. I think I have a small mistake here. I plugged in a -10 there. And what I'm plugging into is the original, not the original, a modified original inequality. And if I were to plug in a large negative number like -10, I'm going to get 4 times negative 10 squared plus 2 times negative 10 minus 1. I'm going to end up with 400 plus 20 minus 1. That's going to be a large positive number. That's bad news for us because our inequality was a less than or equal to, so we exclude interval 1. Interval 2 works. I plugged in 0. I was left with, if I plug in 0 for x, those two expressions go away, and I'm left with negative 1 is less than 0. That's true. So we know that that second interval will be part of our solution. And finally, our third interval will not. If we plugged in, again, f of 10, this would be a positive value. We are looking for negative. So our solution set, I'll just highlight it here while we're looking at it, is in green. It's between our two roots. And on to part D, we factor again. What's unique here is we have one of those double roots. Yes, can't forget about our double roots. So we have a double root here, so things will behave differently. We factor just as usual, and when we work our way through the tests, we just have to be careful. That x squared value is always going to be positive or 0, right? So we're always going to get a positive for our first factor, x squared, and then x minus 9 could be different. When I plugged in into all three intervals, the only one that did satisfy the inequality was my third interval. That third interval starts at 9 and goes to infinity, and because we had a greater than symbol, we use the rounded parentheses. All right, we're going to take a quick look at a word problem and then talk about some rational functions. We've got about 4 or 5 minutes. All right, so here's a word problem describing a basketball being shot towards a hoop, and we are given an equation. Assuming the ball goes into the hoop 10 feet off the ground, when will the ball get in the hoop? We would set this up. Well, this is a height function, so we would say when does 10 equal negative 16t squared plus 14t plus 7. We would solve this as usual. We would set the equation equal to 0. And we would solve by factoring. This is factorable into 4t minus 1 and 2t minus 3. So what that means is that at time 1/4 of a second and 3/2 of a second, the ball is 10 feet off the ground. We would say that the second answer represents, in the context of the problem, when the ball actually hits the hoop. Right, that 1/4 second would be right after the basketball player shot the ball, and the ball goes above 10 feet and then comes back down. Well, that's probably better modeled using an inequality. So that's what we'll do in part B. Construct a modified equation, inequality, that models all times in which the ball will be above the hoop. Well, the height of the ball is negative 16t squared plus 14t plus 7, and we want to know when that height will be greater than 10. Well, here's the good news. We've already done the heavy lifting. We know that in this situation, the ball is shot, it goes up and comes down. We know that at two different locations, 1/4 of a second, and at 3/2 of a second, the ball is at 10. So we know that between that, on that interval, that's when the ball is above 10 feet. So we know that 1.5 seconds minus 0.25 seconds will equal 1.25 seconds. That represents the total time the ball is above the hoop. All right, we'll talk more about modeling later in the week. we are going to finish up here with two rational inequalities. These are going to behave very, very similar to what we did on the last page with polynomials, but we have to account for asymptotes. So I want to just highlight one very important thing in your notes, and that's the last sentence of that paragraph. Due to the nature of asymptotes, we cannot include them in any intervals. All right, so we're going to approach solving a rational inequality the same way we did with a polynomial. We're going to find our zeros and our intercepts, our vertical asymptotes. But even if the sign is a greater than or equal to or less than or equal to, we must always remove the asymptotes from our domain. All right, I'm going to walk through both of these. I'll try to do them quickly. The first one, we can see here if we were to factor 3 times x plus 1, 2 times x plus 2. That just makes it a little easier for me to see those key features. So we know on our number line that something is going on at -2 and something is going on at -1. I'm going to make a note here, dotted line. This is an asymptote. I think it's worthwhile to make sure you can see it, all right? The other point is just a 0, and that's at -1. It still would be excluded because of our symbol. From here, our testing is exactly the same as with a polynomial. So we're going to test on 3 different intervals, interval 1, interval 2, and interval 3. Interval 1, I plugged in -10. And when we plug in -10, we get a negative value divided by a negative value, which is positive. And that's what we're looking for. So that first interval is good for us. That second interval, I used x equals -1.5. And when we do that, we end up with a negative value in the numerator and a positive value in the denominator. That's going to result in a negative number, which we do not want. And then finally, on number 3, interval number 3, I used 0. That's my favorite number to plug in. It's just the easiest. I end up with a positive value. So that means we will include the first and third intervals in our solution. The first interval, -infinity to -2, in union with -1 to infinity. One last problem, one more issue to deal with is if our inequality doesn't start set and equal to 0, right? Like on the first one, we were greater than 0. So what we will do on something like the next problem is we will set that inequality to 0. And what I'm doing here, kind of as we go, is I'm creating a common denominator because if I'm going to find intercepts and asymptotes, I want a single fraction. So I'm going to simplify this fraction one more step. I'm going to be left with -x, right, x minus 2x, and then 1 minus 6, that's minus 5, over x plus 3. And now you can see we've turned this fraction into something much more like what we saw over on the first example. I would also recommend factoring a negative. It just makes the numerator a little bit easier to deal with as far as finding the zeros. You don't have to, but that's just a personal preference of mine. All right, we're going to now set up our test intervals, and we are almost there. We know that we're going to test x equals 10. Sorry, negative 10. X equals -4, and x equals 0. The reason for that is that we have a critical value at -5 and another at -3. I think I forgot my number line here. All right, it would be -5, -3 with our 3 distinct intervals. When we test these, we end up with a, I'm going to include my negative, right, this negative down here, times a negative over a negative. 3 negatives leads to a negative. And that's not what we're looking for. We want positive. Our middle interval will have a negative value times a positive value over a negative value with two negatives. That'll leave us with a positive. That's good news. And then finally, when we plug in 0, we'll end up with a negative times a positive over a positive. That will be a negative number and will be excluded. Now, when we solve this, when we give our solution, we're going to use that middle interval from -5 to -3. Don't forget which term is an asymptote. X plus 3 creates a vertical asymptote, so -3 cannot be included even if we have a greater than or equal to. -5 is a 0, and as a result can be included. Thanks for your hard work today, guys. You are going to go ahead and try the practice problems that I've left for you associated with inequalities, and then if you have extra time, you have the rest of the period to start on your problem set. Thanks, everybody.